The other day I talked about dark matter, and from there I'm going to look at today at some of the groups around the planet that are investigating dark matter. Ooh, this dark matter stuff. Uh, Very important stuff because it's being investigated heavily in many centers, and they're using up a lot of resources. In other words, money. They receive lots of money for these investigations, these researches, and so the question is, where are they now with all these research? Have they advanced an inch, a meter, a mile? How much have they advanced in the search, in the understanding of dark matter? Okay, that's the question. And is your money well spent? And I just want to clarify for you that dark matter has been around for, I'd say, at least 40 years. Okay, the ideas and so on. They were probably there even before them, but for 40 years, people have been investigating dark matter. Okay, so let's find out where these people stand. Let's find out how much progress they have made. I hope a lot. Okay, so here we have. This is what I covered I think a week or so ago. Okay, and what it is essentially I'm saying that dark matter is nothing but an equation. It's a number. It's a fudge factor that they had to put in there to understand how a galaxy rotates or why it rotates the way it does. Okay, that's the issue. Okay, so here it is. These are the equations. Okay, and you don't have to look at all that. I just want to point out the one at the very bottom there where you see v squared equal gm over little r. Okay, that's the one I'm going to look at. Okay, if you want to look at all of this in more detail, you got to go a couple videos back and you'll see the original discussion on this subject. Okay, so what do we have here? Well, we have that little v, and we're going to forget about the squared because that's not important for the discussion today. That little v is velocity, okay? And what is velocity? We're talking about the velocity of a star around, especially around the edge of a galaxy, okay? And the way you calculate that is you take the gravitational constant g, you take the big M, which is all the material, the mass, okay, of all the stars that are within the radius of that star to the center of the galaxy, and the little r obviously is the radius, which is really the distance between the center of the galaxy and where the star is. Okay, so that's what that equation tells you. If you increase the radius, you can see the galaxy on the bottom has the star is farther out. Okay, so the one on the top has a shorter radius, the one on the bottom has a longer radius. Okay, so the radius is bigger. That means the little r on the equation is going to get bigger. If you increase the denominator, if you increase that little r, the v goes down. The velocity should come down. But that's not the case. The case is that when you increase the r, what they observe is that the v goes up as well. And they say, how can that possibly be? That's impossible. Because, you know, if it's farther out, it should go slower, not faster. Why does the velocity increase when the radius increases? That's the issue. That's what they had to explain. So what did they do? They went in there, they said, okay, when I increase the r, the velocity is greater. And so what they did, they created this factor known as dark matter. They created a fudge factor to account for the velocity of a star that is farther out from the center of a galaxy. Okay, so this was the issue. This is how they fixed it. Who fixed it? Physicists? Absolutely not. It was fixed by mathematicians. This is completely a mathematical solution, nothing but. So what is dark matter? Dark matter is nothing but a fudge factor in an equation. That's how it starts. Now, they told everybody, every astronomer out there, and also the people at the particle people, the folks who accelerate particles at the accelerators, they said, go look for it. And so, you know, what does it look like? Well, it's kind of dark and weighs a lot. And so let's look at this. Let's find out, because if it's dark, this is very simple. Okay, very simple. If dark matter is dark and it's around the edge of a galaxy, because that's where they have to put it in order to account for the behavior of the galaxy, the way it rotates with the stars on the outside going faster than the ones on the inside, then they have to sprinkle all this stuff around the galaxy. That's where they have to put it. Okay, and so all this dark matter, it forms like a halo around the galaxy. Okay, it's got to be there in order for the galaxy to rotate as it rotates, as they see it rotating today, and to explain why a star at the edge travels faster than the ones on the inside. That's the argument. Okay, okay, so what did they have to explain? Here it is. Here's the graph. This is mathematics, but it gives you an idea because it's superimposed upon a galaxy and the stars on a galaxy. And what you're going to see here is that the farther a star is from the center, the faster it goes, which is very counterintuitive, right? And here it is. You can see what they expected. That's the one expected from visible disk. as you go farther out, the distance, the speed should go lower. Okay, so the more distance, the speed should come down. That's not the case. What observations show is that as you go farther out, the star goes faster. How did they fix the problem? Oh, very simple. They fixed all these problems very simple. And what they did, they sprinkled all these kilograms on the outside. Okay, so now you have all these kilograms, very heavy kilograms, by the way. And by doing so, they fixed the problem. They were able to imitate what they observed in the night sky. Okay, so this was the issue. This is how dark matter came into being some time back. And that's where we are today. So again, they told all the astronomers, go look for it. They told all the particle physicists, go look for it. Now that's what they're all doing. They're spending your money looking for it. We wish them good luck, obviously, right? Okay, so here we have the halo. And again, this halo is on the outside of the galaxy. Okay, keep that in mind. But you can imagine, how can I explain this? You have all this dark matter on the outside, right? It's heavy. They say it's dark. We can't see it very well because it's the night sky and there's no contrast there. Okay, so what's the problem? If this halo, which extends far beyond the edges of the visible part of the galaxy, right? Extends way beyond that. If that halo is there, if a star goes behind this halo, you should be able to see it right through the halo. I'm sorry, you should be able to see that star through the halo because the halo is there in its way, if it's dark matter. Okay, and so here it is. This is what the halo looks like. Okay, this is the drawing, by the way. This is not real. Okay, this is a drawing. It's an imitation of what the halo they think looks like. Okay, here it is. Sorry, I gave you the wrong one. It should be the other one. I think it's this one. Yeah, this is what it should look like. Okay, halo. But the one I showed you just now, which is this one, this is what it does look like. In other words, you can see right through the halo and see the stars at the edge of that galaxy. Stars are in the background, in other words. So we don't see this, which is what they explain, what they describe. They say, look, there's a halo around the galaxy. Okay, fine. Why can't we see through the? Why can we see through the halo? Why is it that the halo doesn't block out the stars that are behind in the region of the halo? That's the question. And this is what we see. And this is what they explain or what they describe. Okay, that's where the problem arises. Okay, so we can't see through the halo, and so the question is whether maybe we're looking for angels and ghosts out there. You know, Casper, is that what we're trying to see? Okay, so this is the issue. The issue is that these people are saying, you know, there's a halo there. It's dark matter. Fine, great. If it's dark matter, it should block out any star or any galaxy that falls within that behind the halo. You shouldn't be able to see through the halo because it's dark matter. Maybe they should call it transparent matter or translucent matter because we can see right through that so-called halo. So what is this? Invisible matter? Are they looking for ghosts? You know, I mean, they're doing a lot of equations in their offices. And the question is, how does that match what we see out there? And they're saying, well, here's the equation that explains why stars on the outside of a galaxy travel faster. Yeah, that's great. That's maybe one solution. Maybe there's another solution. And what they say, what else could it be? It's got to be some kind of dark matter there. Well, if that's dark matter, why can we see right through that dark matter? Maybe it's not dark matter. Maybe it's translucent or transparent matter. Maybe we got the wrong name for this dark matter thingy. Okay, so here are the numbers. This is where your money's going. So pay attention. They're stealing from your bank, okay? And I want you to see that, okay? Here we have the Department of Energy of the United States. And this is just the year 2020. They do this every year. But in 2020, they spent $132 million, right, for high energy physics research. Okay, what does that mean? What is high energy physics research? Well, there at the bottom you see it. Higgs bosons, right? Neutrinos, dark matter, dark energy, and search for new physics. That's what all that money's going to. And it went to 64 universities who, you know, people apply for these funds and they say, I'm going to be doing research on dark matter. Oh, okay, and I need $10,000. And so the guy justifies it. They give him $10,000 and then they move on to another university and do the same thing. So they spent $132 million, 64 universities. That's like, 20 million per university on the average, more or less. Okay. And this is where your money's going. Okay, and let's find out what are the results of this. I mean, this was 2020. They've been doing this at least for 40 years. Okay, so what are the results of all this stuff? Well, here's NASA. Okay, I mean, NASA receives a lot of the inputs from universities and so on. They have And they also fund a lot of these universities as well, especially for these types of projects. And here's NASA, okay? Dark energy, dark matter. This is from their site. This is from NASA's site. And it says, we are much more certain that what dark matter is not than we are of what it is. This is after 40 years, folks, okay? We know what it's not what it is. First, it is dark. Well, if it's dark, why can we see the stars? Why can we see the stars in the background behind the halo if it's dark? Maybe they should have said it's invisible or it's translucent or transparent, meaning that it is not in the form of stars and planets that we see. Okay, observations show that there is far too little visible matter in the universe to make up the 27% required for the observations, because they say that dark matter constitutes 27% of the matter in the universe. Okay, and they say the visible stars, the visible stuff, doesn't account for that weight that they need to make the equations come out right. That's what they're saying there. Second, it is not in the form of dark clouds or normal matter, matter made up of particles called baryons. We know this because we would be able to detect baryonic clouds by their absorption of radiation passing through them. Okay, and how come they don't check the radiation passing through the halo? Okay. Third, dark matter is not antimatter because we do not see the unique gamma rays that are produced when antimatter annihilates with matter. Great. Finally, we can rule out large galaxy-sized black holes on the basis of how many gravitational lenses we see. In other words, light is not bent around the dark matter. Okay, so that's what they're saying. So they can't put a black hole in that same region. High concentrations of matter bend light passing near them from objects further away, but we do not see enough lensing events to suggest that such an object to make up required 25% dark matter contribution. So it doesn't do that lensing thingy, that Einstein invented, the Einstein lensing, that the star or the black hole, and because it's a collapsed star, a bunch of mass there, invisible mass, supposedly bends light. But they don't have that same situation with the dark matter. You don't see light bending around a galaxy. And so they can't say, well, there's a black hole there that we can't see either. No, they can't do that. So they had to invent dark matter. They invented a new variable. Lots of mass, conveniently dark, better yet, invisible, intangible, what you can see through it. It's translucent, transparent. You figured it out, okay? Okay, here's CERN. This is the one here in Switzerland. Okay, they do accelerations. And they're in the dark matter business as well. And these are their numbers. These are the countries that put money to keep CERN running. By the way, the United States also puts money into this. Okay, but it doesn't show up here because this is like their regular budget. But the United States has donated quite a bit of money to CERN as well. And you can see there, it's quite a bit of money. Okay, we're talking in the billions. Okay, not in the millions, but in the billions. And this is their budget. Okay, or at least this is the money that's coming into CERN. What percentage of this goes to dark matter, I don't know, but right now there's a lot of research going into dark matter. Okay, so this is something you got to consider for any understanding of this dark matter thingy. Okay, and so that's the money. What has CERN produced with all this money? Well, let's find out. Here's what CERN has produced over the years. Okay, so very important. Find out if you got your money's worth, okay? Here it is, dark matter. This is directly from CERN. Invisible dark matter makes up most of the universe, but we can only detect it from its gravitational effects. Well, are you sure it's a gravitational effect? Could it be an electromagnetic effect, maybe? Okay, I mean, I'm just suggesting, right? Okay, not trying to shove gravity down your throat like you are trying to do with me, okay? Galaxies in our universe seem to be achieving an impossible feat. No kidding. Under gravity, it should be an impossible feat. They are rotating with such speed that the gravity generated by their observable matter could not possibly hold them together. Okay, yeah, if you want to hold something together, you need some kind of elongated thing that holds the stars together between them. You need interconnectivity. That's what you need. Then you can talk about why they're together, why a star doesn't fly out or is flung out of the galaxy. They should have torn themselves apart long ago. Absolutely. If you're talking about discrete particles, there's no reason for any galaxy to remain in a single piece. The same is true of galaxies in clusters, which leads scientists to believe that something we cannot see is at work. That I don't doubt. It's something you cannot see. For those of you who insist on see and touch, well, there you see. They can't see the stuff. They think something we have yet to detect directly is giving these galaxies extra mass, generating the extra gravity they need to stay intact. Well, it's not gravity. It's what it is all atoms are interconnected. Then it's very easy. And yeah, you can't see it. So don't look for it with your telescopes, please. This strange and unknown matter was called dark matter since it is not visible. Well, yeah, but again, if you can't see through the, I mean, if you can see through the stars right through the halo, then maybe the word dark is wrong. Maybe it's invisible, translucent, transparent. Those are better words for that type of matter. Okay, and yeah, it's conveniently heavy and conveniently dark. So you can't see a contrast between space, empty space, which according to relativity is a physical object also, but that's a secondary issue. But there's no contrast between the dark matter and space, black space, dark space. Okay, transparent space, translucent space. Okay, here's the Australian Research Centre. Okay, another group that heavily investigates, this dark matter thingy, and it's the Australian Research Council. You can tell there by the jumping kangaroo. Dark matter explained. They're going to explain to us dark matter. So finally, I guess our money is finally invested properly because we're going to get an explanation. It says, dark matter, it is a mysterious substance that holds galaxies together and contributes 84% of the matter of the universe. Its existence is inferred from its gravitational interaction, and the exploration of the nature of dark matter is considered science's next frontier. And let's see what it is. It says the existence of dark matter has been established by many astrophysical and cosmological observations. They say that you can't see it, but they established it through observation. So what is it that they observed? Maybe they observed visible matter and not the translucent dark matter. Since dark matter cannot be seen directly, there it is. They talk about observations, they say you can't see it directly. Its presence is inferred, and they call that an observation because they infer from its gravitational influence on other objects. Okay, well, maybe it's not that, maybe we have to figure out what gravity is. Maybe it's interconnectivity. Maybe all the atoms, maybe all the stars, maybe all the universe is interconnected, all the matter in the universe. Then we could find out, how you do action at a distance. But yeah, if you just talk about numbers and say mass does this and gravity does that, well, yeah, then and force and so on, well, yeah, then you're talking about concepts. And you cannot explain a physical mechanism with concepts. However, the identity of the particles that make up this dark matter is unknown. No kidding. Well, what are they? If they're particles, we're done. Just talk about grains of sand, right? And what, each grain of sand weighs 1,000,000 tons? And that's what you're going to sprinkle out there? And then again, how do you explain with that, assuming that's the case, right? How do you explain with putting grains of sand that weigh tons and are invisible, right? Translucent, dark, whatever. How do you explain that one star does not fly out of that system? What holds it there? Mass? Is it gravity? The concept gravity, is that what holds it there? No, you got to have some physical mechanism. That's what these people never were able to first make an assumption of and then to explain. They don't have a mechanism. To find out what dark matter is, well, all you have to do is just tell me. Just tell me what it is. We need to propose new theories of what dark matter could be and test those ideas. So how are they going to test ideas? You got to make an assumption. That's what you need to do, and you don't test assumptions. What you do is you make an assumption so that you can explain your theory of what keeps a galaxy, compressed. It doesn't fly apart in pieces. That's all you need to do. And so what is it? They're saying they don't know what dark matter is, but they're going to find out. Well, you've already decided that dark matter is a bunch of heavy particles that are invisible, dark, translucent, whatever. You've already decided that. So we know what dark matter is. It's a bunch of particles. And we know that also because all these centers like CERN and SLAC and Fermilab, they're all looking for it in their accelerators. What are you accelerating? What do you expect to find? Well, you expect to find particles. So we know what dark matter is. According to your mentality, it's particles that are very heavy and they're dark. Okay? That's it. We know what it is. So what is it these people have been doing for 40 years, trying to explain dark matter and that they don't know what it is and just gobbling up money, investigating something that they're still looking for because they don't know what it is? It's just a circular argument. What are these people up to? Okay, here's the Cambridge Cavalier Institute, another famous, important dark research center. I'll call it a dark research center. I like that. And it says, despite abundant evidence of the presence of dark matter in the universe, the direct searches in laboratories have found no viable candidate that would explain the dark matter. Yeah, no kidding. Okay, I like it because it says nature of dark matter. That's the title of this. It is thus increasingly important to explore astrophysical and cosmological probes of the nature of dark matter. Yeah, no kidding, especially with my money, right? Currently, the most stringent constraints on the nature of dark matter candidates come from studies of the clustering of the intergalactic medium in spectra of distant quasars. Remember, what they're saying is they're looking for stuff that's between the galaxies. That's what they want to, that's where they focus, maybe their telescopes or whatever, to see if they can see something there between the galaxies because they're few and far apart. in comparison to like stars or planets. Okay, the distribution of gas and stars are a potential observable feature that could help unravel the nature of dark matter. So what do they have? Well, they have the astronomers looking at the skies with their telescopes, and they have the particle mathematicians accelerating particles, trying to smash them to see if they can produce dark matter in their cauldrons, and you're funding all this effort, and they don't know what it is after 40 years, when they already know what it is because they're saying it's particles, they're heavy, they're translucent or whatever, dark, so they know what it is. So just tell me what it is. Tell me that they're particles, that they're heavy, they're round, maybe they're square, I don't know, cubic, and I guess they're 3D, right? They weigh a lot, and dark, maybe translucent, transparent. We're done. We know what it is. What do you mean you don't know what it is? If you already decided what it is, because that's what you need to put weight, sufficient weight, mass, in your equation for the equation to come out right. In other words, meaning that the equation now matches what you observe of visible matter, meaning the stars don't run out of the galaxy and the stars on the outside travel faster than the ones on the inside. Okay, so this is the issue. Okay, and here in Frankfurt, hey, we don't stay behind. You think we're dumb here or what? We have here Sabine Hassenfelder, and she works at the Frankfurt Institute of Advanced Studies. In fact, close to my home here in Frankfurt. And she's known as her title is a theoretical physicist. I don't know what a theoretical physicist is. Either you're a physicist or you're a stamp collector. No such thing as a theoretical physicist. We're all theorists. That's what a physicist is, a theorist, whose research focuses on the phenomenology of quantum gravity, whatever that is. What they're trying to do is merge, again, relativity with quantum mechanics, and that's what quantum gravity is. It's a euphemism for that, I guess, figure of speech. And here's the key one, and superfluid dark matter. What the hell is superfluid dark matter? Well, it's whenever you see superfluid, okay, there's no friction. That's the point. And usually you get that at very low temperatures, okay? So that's why they use that word superfluid, that adjective there. Whenever you see superfluid or super whatever, they're talking about frictionless matter, meaning usually at very low temperatures, okay? That's what the supercomputers are also all about. Okay, she studies the role of Lorentz variance and locality, which would be altered in the discovery of quantum gravity, a topic that she has been trying to find experimental evidence for. She is the author of Lost in Math, How Beauty Leads Physics Astray. And I think that's a good way of putting it. I think this lady, you have that situation there. Beauty leads physics astray. And that would mean that she also thinks she's beautiful. Okay, I guess that's what she's implying with that. Beauty leaves physics astray. Love that title. Okay, and so what does Sabine talk about? Okay, and this is what she's proposing. Okay, this is a summary of what she's proposing. Superfluid dark matter plus modified Newtonian dynamics, which was created or invented by this fellow, Jewish fellow, Mordecai Milgram. And she says recent studies have shown, recent studies meaning her, okay, by the way, that dark matter with a superfluid phase in which phonons, remember we covered phonons? What are phonons? A bunch of vibrating particles that vibrate somehow in unison. Okay, that's called a phonon. It's a particle of sound. So a particle of vibration, okay, mediate a long distance force, gives rise to the phenomenologically well-established regularities of modified Newtonian dynamics, MOND, which is, again, it's a modified Newtonian equation that Milgram came up with. Superfluid dark matter, therefore, has emerged as a promising explanation for astrophysical observations by combining the benefits of both particle dark matter and MOND, meaning the modified Newtonian dynamics, or its relativistic completions, respectively. Our analysis demonstrates that superfluid dark matter fits the data well with parameters in reasonable ranges. Okay, so she's got this duality. She's introducing, on the one hand, a modified equation for gravity. She's saying that gravity out there at the galactic level does not behave like gravity here on Earth. That's the first one. That's what Mond says, okay? And then parallel to that, she's introducing this superfluidity, which means that it's a frictionless matter. That's essentially it, okay? Does she know what dark matter is? I'm sure if you ask her, and she's been studying dark matter for at least 20 years, I would say, she wouldn't be able to tell you. And here I'm telling you what dark matter is. Please listen to me. I'm telling you what dark matter is. It's particles that weigh a lot and are invisible. See how simple it was? That's what dark matter is. And I don't know what they're trying to do. What are they? They're trying to find it out there. They can't see it. So why are they putting their telescopes between galaxies to see if they can see it, if they're already telling you that it's invisible, it's dark, it's translucent, whatever, weighs a lot, and it's particles. It's a bunch of sand that weighs tons of kilograms. Okay, so we're done. I mean, we know what dark matter is. So I have an analogy for you, okay? And it's known as the Schrodinger's black cat analogy. It's the Schrodinger black cat and the Klingon, okay? And this is, I think, the perfect analogy for what you're seeing with dark matter, okay? If you bear with me, I'll carry you through the fable, okay? This is a fable, okay? And so here's Erwin Schrodinger. He encounters a Klingon, okay? Klingon comes from outer space, and Schrodinger is going to talk to him about his black cat, which apparently he lost, okay? So here he's going to try to explain to the Klingon, okay, that about this cat. He says to the Klingon, he says, I'm looking for a cat. Can you help me find it? And so the Klingon says, what's a cat? Okay, and so Schrodinger goes in there and says, well, I don't know. I have no clue. And so the Klingon says, well, what's it look like? Can you at least tell me what it looks like? He said, well, all I know is that it's black. Well, okay, not much to go on. So the Klingon said, well, where did you lose it? And he says, I lost the cat in a dark room one night. And he said, well, where's the room located? And Schrodinger says, well, look, it's on the other side of town, some 15 miles away from here. And so the Klingon says, well, how am I supposed to find it? I mean, how am I supposed to help you find this cat that you're talking about that you don't know what it is, which is apparently black? The only thing you can tell me about him, and you lost him 100 miles away, and how am I supposed to find it? And so Schrodinger says, well, here's a microscope that you can use to look for it. And that's essentially what the story of dark matter is all about. Okay? That's in a nutshell, dark matter for you.